Swayam Prabha. Digital India. Educated India.
Welcome to Module 6, Lecture 1. In this module, we shall be looking into strength of concrete, and as we know that concrete is a particulate system, bonded particulate system. So, your particles are there which are bonded, largely mechanical bonds, and therefore, it is not very strong in tension. You can pull it apart easily, while if you push, it is relatively stronger, it can take lot more load. So, therefore, when we talk of strength of concrete, our main thrust or emphasis is on compressive strength of concrete. However, we will be discussing about tensile strength of concrete as well, all right, and tensile and similar other properties, related strength properties as well. So, therefore, general outline is of course, cube strength. I will mention why cube strength quickly, then fracture mechanism, and therefore, what affects the strength, the mixed parameters largely or basic mechanics, so mechanism of failure and all that we will look into in this lecture. Strength of concrete is needed for structural design, and usually we determine it through specimen testing. Since concrete is a structural material and we make structure out of it, therefore, it is required for structural design. Strength of the concrete is required, because safety is a primary issue. So, we determine strength of concrete by specimen testing, and determined strength depends on specimen type. It depends on specimen type, it depends on specimen type, and of course, also on test conditions. For example, strength of cylindrical specimen is lower than cube of same concrete, and in situ cube strength in structure is lower than both. So, you see, it depends upon types of specimen you test. In Indian scenario, we do test cubes, and that is why this heading cube strength, that is why the heading cube strength. Not only in India, Europe, UK of course, from where that the concepts of cube strength came to India, they do use cube. Largely North America and even North and South America and Japan, those countries use cylinder. So, it is a type of specimen, that is very important, and we test the specimen, and test condition also affect the strength, that is the first. Now, in situ strength can be related to the cube strength, whatever is the cube strength, it can be related to the strength in actual structure in some manner, and therefore, cube strength is a relative measure of the mix that I am using. We have looked into mix proportioning and its making totally, the casting, the procedure of production and all that. So, basically cube strength, since I am preparing it separately, not taking from the structure, cubes are prepared separately, specimens are prepared separately, and that is not taken from the structure. Therefore, cube strength largely measure the relative strength potential of the mix basically. So, it is relative strength potential of the mix proportion only, and structural strength in the structure is somewhat different. But this strength potential or relative strength potential can be related to actual strength one can expect in structure for the design purposes in some manner, and therefore, can be used in structural design as such. Let us see, if I look at a cube, how does it fail? You see, this is the failure pattern of uniaxial failure pattern. That means, I have applied some sort of load on a cube, in a cube specimen. This is for the cube specimen. So, since in Indian scenario largely we test only cubes, we will be talking more about the cube strength, and many other countries do follow the same. So, in a cube actually you will be applying load through machine platens, maybe that is a circular one, and you apply load like that, and the reaction comes from the bottom, reaction comes from the bottom, reaction comes from the bottom, and once you have applied load and made it to fail, it will fail like this. So, this is a kind of failure plane. You can see this is a typical failure plane taken from photograph, and you can see this is for normal concrete. So, your aggregates are exposed, aggregate surface are exposed, and actually crushing of aggregate has not occurred here. So, this is typically the uniaxial failure of cube, and this is another diagram from another side, and all shows that aggregates are exposed, they do not fail in normal strength concrete. So, failure through aggregate boundary rather than through them, and you can have multiple visible crack, and this is the shape of the failed specimen as we have seen, shape as we have seen. Now, we will explain this, why this shape we get it, but one thing we must like to understand from here is that in normal strength concrete, failure is through the aggregate boundary rather than through the aggregate themselves. Actually, fracture plane therefore, would be passing like this at the aggregate boundary, and maybe passing through some mortar and then again through aggregate boundary. So, if we take a portion of that fracture plane, uniaxial compression failure, fracture plane in normal strength concrete will look like this. These are the aggregates and the mortar around, and you can have multiple of course cracks here and there, etcetera, etcetera, but failure plane finally as a fracture occurs, it would occur through this kind of a situation, it will break through the aggregate boundaries. So, that is normal concrete, fracture plane passes through boundaries, aggregate boundaries. What are the phases in concrete? So far we have looked into aggregate is one of the phase, it is very strong in normal strength concrete. In high strength concrete of course, you try to attain the paste strength such that it nearly matches with that of the aggregate strength, and thereby or whatever other phases, all other phases, strength of all other phases almost matches with that of aggregate. Therefore, aggregate may also fail in high strength concrete, but normal strength concrete up to let us say 60 MPa concrete, aggregate normally does not fail, the failure is through the aggregate boundary. And the phases, other phases present in the concrete is the paste phase. So, it is the paste phase, phase is the paste phase, this is the paste phase. So, paste aggregate, when I say coarse aggregate as well as a fine aggregate. You can, as you have seen earlier, it is aggregate and mortar, and in the mortar again the paste and the fine aggregate system. So, paste can be considered as a phase, but one actually can identify and another phase. Well, it is not a phase, but it is a transition zone between the aggregate and the paste phase. All right. So, this we call as interfacial transition zone, we call as interfacial transition zone. So, this is nothing but your paste boundary. If this is your aggregate, this the boundary of the boundary of the like you will have some, this is your bulk paste, let us say bulk paste. So, this is the boundary surrounding, and this could be something different, this could be something different, this could be something different, this could be something different. For example, this could be the bulk paste phase. So, this is about, so this is my, this I can call this as bulk paste, aggregates, and there is a transition zone which is about 30 micron thick. This is called aggregate paste interfacial transition zone, aggregate paste interfacial transition zone, and because this is not smooth, here aggregate, there is a bulk paste, but there is a transition zone between these two, and this is roughly about 30 micron thick. So, this is you can call it as a phase, and this is very important. So, you have got actually aggregate, and then you have got paste, and then you have got ITZ, you have got ITZ. The paste aggregate interface has properties different than either bulk paste or aggregate, and is called ITZ. So, it is different than the bulk paste itself, it is different than bulk paste itself, or aggregate itself. So, it is different than paste and aggregate, and which that is why you call it, define it almost as a separate phase. Now, why it is, we will be able to actually understand gradually, we will be able to understand it gradually. Now, strength of paste is attributed to cohesion, paste, because CHS gel. So, between the gel particles across gel water, cohesive forces, something of the van der Waals kind of forces exist. So, you see the strength of the paste. So, paste, if you want to separate out, you have to actually break this cohesion force. So, therefore, paste strength could be quite high. Large discrepancy of course exists between the theoretically estimated strength calculated from bonding forces and observed fracture strength. For example, if you calculate, if you get x strength from theoretically strength from theory, why? How? Because strength per bond is known, strength per bond is known. The van der Waals bond, van der Waals kind of bond, van der Waals bond. So, I know strength per van der Waals bond, and if I also know number of bond per unit area, then I can calculate out the theoretical strength. So, I got to know actually number of strength from theory, that would be actually strength per unit bond, and if I know number of bond per unit area, then I can find out strength per unit area. So, I can find out strength per unit area. So, that is your x, let us say. Now, this can be estimated theoretically. What has been observed is that theoretically estimated strength is 10 to 1000 times more. So, this x theoretical or whatever you call it, sigma theoretical let us say for tensile strength is theoretical is 10 to 1000 times more than sigma actual. So, therefore, there is a large discrepancy, whatever theoretically you calculate does not actually exist. So, why it is? The difference had been attributed to existence of cracks and flaws within material even before any load applied. So, even before you have applied the load, the material is not absolutely homogeneous. If you have just the paste, even the paste is not all solid, there could be some flaws. If they are not cracks can come from shrinkage and similar sort of thing, but the other kind of flaws would be there, which are inherent to the system. For example, capillary pores and gel pores of course does not take part, it is too small to influence in a significant way the strength, but it can still influence. Largely it is the capillary pores which are the flaws within the material. So, this difference that comes in 10 to 1000 times, that is essentially attributed to flaws or pores within the material. On tensile load application at a critical state, fracture initiates from existing cracks or flaws and propagates spontaneously when rate of strain energy release is higher than rate of energy required to create new fracture surface. Okay, what is failure or what is fracture? What is failure? Failure means material is getting separated out under tensile load, let us say. So, if we have some material and I am applying pull from this side, pull from this side, somewhere the material gets separated. So, this is material is getting separated. Now, this separation means creating new surface. So, you are creating a surface here and creating a new surface there. So, it is actually now kind of a new surface and kind of new surface is being created, which is matching of course. So, by pulling them apart, you have actually created two new surfaces. Now, each surface is associated with kind of surface energy. There is an interface between solid and liquid, or solid and air, or air or liquid. At the interface always there is some sort of energy associated with it, because the material here will be here will be pulled. It will be interacting with materials along all directions, where one in the surface it will have cohesive forces which will pull, which will get it, the other particle on the side or the solid side will pull, whereas here there is no such material. So, there is a kind of a surface energy existing at the surface energy exists at the surface, and this occurs to any interface. So, since there is a surface energy required at the surface, to create a new surface you must provide that surface energy. And where from this energy comes? In case of fracture or failure, you are applying load, which means that you are applying stress. This is causing a strain before failure. So, this half stress into strain is actually strain energy, and when the strain energy supplied is high, or rate of strain energy supplied is high, and is released is higher, then rate of energy required to create new fracture surface, fracture will propagate spontaneously, and this is what was actually postulated by Griffith somewhere around 1918 or so, around that time, maybe second half of the second decade of 20th century, when he was looking at the as a failure of glass or such brittle material. So, decrease in strain energy for elliptic crack of length 2 C1 in a plate of unit thickness is considered together with surface energy. So, that is what he did. So, let us see what did he do. Well, I think I will come back to this diagram, but let me look at one more diagram slightly later, and then I will come back. I will just come back again to this diagram. Yeah, for example, this one. So, if you have a hole and you try to, in this one it is showing compression. Supposing I try to pull it along this direction, supposing I try to pull it along this direction, I try to pull it along this direction, pull it along this direction, pull it along this direction. So, let me go back to my earlier slides itself, and let me just draw it for the sake of explanation. Supposing I have got a surface something like this, there is a hole and this is my material, there is a hole, and I am pulling this material from this side, then what will happen? This crack will try to expand. Now, if this crack tries to expand or this hole tries to expand, the fracture propagates along this direction, right. So, fracture propagates along this direction, that means it creates new surfaces here, Now, the stress around a hole, for an elliptic hole, one can estimate stress concentration around an elliptic hole can be estimated from elasticity theory. And if you apply more load, what would be the further stress, that one can find out, and correspondingly the strain energy one can find out. Expression for strain energy, these are available from available solutions of elasticity theory, these are already available, and then the rate of strain energy change with this crack width 2 C 1, 2 C, 2 C L if I call it. This was actually determined, and from this if you equate that rate of strain energy, in the limiting case rate of strain energy release is equal to rate of surface energy required. So, if you equate this, you can find out what is called a critical stress. So, you can find out what is called critical stress. So, critical stress is that stress at which the fracture will propagate spontaneously. So, that was the idea. So, this is the released energy pi c square sigma square, and half crack length is c in this particular case, and 4 C T is the fracture energy. So, because why the T is the surface energy and thickness is taken as unity. So, it is a you can assume there is a plate sort of a thing which is under tension with a unit thickness. So, the area would be two surfaces if you want to create, if you half crack width is 2 C. So, crack width itself or hole itself is 2 C, its width will be 2 C. So, this is your elliptic crack, this is 2 C, this is 2 C into the thickness T which is unity. So, into 1 and this side again 2 C. So, 4 C T is the surface energy per unit area. So, 4 C T is the surface energy, 4 C T is the surface energy, right. Now, required surface energy, because 2 C is this full length, C is half C, crack width is C, C is half crack length. So, 4 C T, and correspondingly from the stress concentration concept, from theory of elasticity one can find out pi c square sigma square by E is the released energy. So, when rate of this one and rate of this one is same at a given C, at that C the stress for a given C is known to me. So, sigma corresponding to that C would is a critical stress. So, let me just differentiate this will come as twice pi C sigma square by E, and that must be equals to 4 T. So, if I take this force if I take this rate of strain energy release, this is this situation rate of strain energy. So, at this stress, at the stress corresponding to this point is a critical stress. So, therefore, you can actually by E, this is by E, this is by E square, this is by E and therefore, you can find out sigma is equals to, this will be 2. So, 2 T E divided by this is cancelled out pi C everything under root. So, critical stress is 2 T E pi C everything under root, where C is the half crack width. So, you see this is what this corresponds to this state, where the strain energy release rate is equals to this slope at this length, the rate of strain energy release is same as rate of strain with respect to C, of course. So, that is critical stress, that is critical stress, that is critical stress. So, sigma T is equals to 2 E T. So, you can see the critical stress at which fracture will propagate spontaneously is a function of the half crack width. Now, if already some crack or holes are existing, they would behave like that. So, in other words, this you can think of in terms of, if there are, you see this is the critical stress sigma T, elastic modulus, energy required to create new surface, and this is the crack length. You can say this is the crack length of the elliptic crack. So, it is under tension, this is under tensile forces, this is under tensile forces, this is how it will behave. In other words, this plays a major role, this plays a major role, this plays a major role. So, if already some holes are existing, and if already some holes are existing and their dimensions, so larger the dimensions, less will be the critical stress. So, they will start actually fracture will start propagating from them at some stress, that is sigma T. Now, in concrete you have lot of capillary pores, and therefore, multiple cracks would actually generate, multiple cracks will generate. So, this is your required energy line. Here it will not be a single not will be a straight line, because it will be sum total of number of straight lines. So, therefore, because there are number of holes and corresponding to, for example, at some sigma 0 at this is C 0 cracks will start propagating, at some other sigma 1 cracks will start propagating from smaller sized voids or holes or pores that are existing, and so on and so forth. So, that is for the actually multiple cracks in concrete. So, multiple holes in concrete, and from there actually crack starts propagating. So, largest hole, the crack will start propagating from largest hole, even if there is no shrinkage cracks. If there are shrinkage cracks, from there it can propagate. Whatever is the largest holes or flow in the material, from there the crack would start propagating, and then possibly join the mortar, cracks in the mortar, which also might start which I mean more other cracks somewhere else, and once they join all together, the failure or overall fracture occurs. So, that is how the mechanism of failure of concrete, and this we can understand. Supposing I apply tensile load to concrete, it should ideally fail, uniaxial tensile strength, ideally it should fail like this, and this load is directly, if I have been able to apply, this is because this is a brittle material. So, it is weak in tension, because particle bonds are not very strong, So, this is weak in tension, and if you look at uniaxial compression, applying load like this from this side to this and this side to this, uniaxial compression, it might develop multiple fracture, ideal uniaxial compression, because material is strong in compression. Okay. Just go to the next diagram, and then we will come back again. Supposing I apply biaxial, both these sides, force from this side, force from this side. Now, what will happen when I apply force from this side? It will actually material will try to move away in this direction, and when I push it, because from this side also material will try to move towards this direction, therefore, you will have cracks like this. So, in case of cubes, whenever you are applying load, the material has a tendency to move along this direction because of Poisson's effect. Material has a tendency to move along this direction because of Poisson's effect. Material has a tendency to move along this direction because of Poisson's effect. If it is biaxial, applying load like this, this will be further moving. So, in biaxial case, you can see the cracks are vertical. That means, material is trying to go away along this direction. So, tension acts along this direction, and crack comes because of tension. In this one uniaxial, therefore, crack can come in both the direction. Uniaxial compression, crack can come in both the direction. And if you now recall the situations where you had actually seen from both the sides, we have seen the failure plane were looking like this, both the sides. Both the sides it was looking like this. You had something of this kind. If you remember, the failure plane that we have seen earlier were something of this kind, something of this kind. Failure plane we saw in case of concrete were both the, because under uniaxial compression, material will try to move in both the transverse direction, and the concrete is weak in tension. Therefore, it will fail, while if you apply from all three direction compression, you can really do nothing, it will not fail so easily. If you apply compression from all three directions, apply compressions from all three directions, this side, as well as compression from all the sides, triaxial situation, it can withstand good lot of load. Physically, you can understand what will happen if you try to compress it from all the sides. Simply the voids will get they will get reduced, possibly all particles will come close to each other. Now, after that crushing at atomic level is not possible. So, it can take actually enormous amount of load under triaxial situation. All right. Biaxial, of course, because there is no tension. So, anyway, that is separate issue. So, it can take much larger load under triaxial situation. Biaxial failure will be like this, uniaxial failure will be like this. So, failure of concrete, therefore, we understand even the compression failure essentially is occurring not really by compression, but because of the tension in the transverse direction. Let us see something more, tension in the transverse direction. So, this is what it is. Supposing you are applying compression like this, there will be tension along this direction. So, if you have a capillary pore, large pore or large fissure or kind of a crack or whatever it is, actually the crack will propagate in this manner, crack will propagate in this manner, right, even under compression. And this, once the crack has propagated up to this, or this, this is the 2 C. So, you can see the compressive strength is also related to sigma T critical that we talked about. So, uniaxial compressive strength will be related to critical stress that we talk about, some or other. I mean, it is not very easy to model them, but it will be somehow related to the sigma T. That relationship perhaps is not so easily understood. It requires, perhaps it will require more research. So, that is it. So, therefore, what we have understood so far, just quickly trying to relook at it. Failure of concrete takes place through aggregate interface in normal strength concrete. High strength concrete can occur there. So, we will come back to that interface a little bit more. An interface exists, which is a transition from aggregate phase to the paste phase around 30 micron. If you look at the failure of concrete, the failure occurs at the aggregate boundary. So, therefore, there is a phase which we call it interfacial transition is important. Also, we looked into what could be the failure mechanism. We have seen that in such material, theoretically estimated strength is much higher than actually that is realized, and this must be because of some kind of flaws. So, stress concentration around flaws or holes existing, that one can look into, and fracture process can be thought of as generating new surfaces, creating new surfaces which require surface energy. So, rate of strain energy release, if it is more than that required to create new surface energy required to create new, fracture will propagate spontaneously under tension. Now, concrete under compression also fails in tension in the transverse direction, and that is what we have just looked into. So, we will follow it up further, let us just look into more of it. So, crack growth in compression due to transverse tension, that is what is most important to understand. So, therefore, if we look at the previous one, it was sigma T was something like under root 2 E T divided by pi into C. So, C is the half crack width, and if we assume that we do not have really shrinkage cracks in the situation, shrinkage cracks has not occurred, which actually do not necessarily, not large shrinkage crack will not occur in concrete, then this C would correspond to something like a pore radius of the flow that is existing. So, it will something like pore radius. Therefore, some sort of a measure of the pore radius if I have, C will be related to pore radius. T of course, is surface energy. Now, E is modulus of elasticity of pore free solid, and surface energy is also that of pore free solid, right. So, therefore, if pore free solid I consider and I find out sigma 0 for the pore free solid, for a porous solid it can be simply related to these portions, can be actually related to these constants etcetera, can be related to sigma 0 into 1 minus p, because more the porosity, this effective E would get reduced, effective T would also get reduced. So, this is simple model, actually that could be much more complex model, but one can fit in empirical kind of relationship of compressive strength with some sigma 0 1 minus p into another constant. Now, sigma 0 is also is a strength at 0 porosity, which is almost difficult to determine. Rm is a measure of average or some kind of a mean pore size or some sort of mean pore size. This tells us that it would be inversely proportional to the pore size. So, simple relationships of this kind were tried out, and this is called average pore size, mean distribution radius is called mean distribution radius, where V I is the volume of pores corresponding to R I radius. So, this is the sum total of all volume of pores, and this is actually logarithmically. So, this is logarithmically ln R I. So, mean logarithmic pore radius, because pore radius varies in logarithmic scale. It will vary from, as we shall see, from nano size to fraction of millimeter size. So, over a large range, so it is better to express them in logs in logarithmic scale, and this is the log mean radius is weighted average with respect to volume. So, something of this kind, this is called mean distribution radius. So, sigma t, if you recall, was something like this, and therefore, one can possibly write E 0 T 0, where E 0 T 0 stands for pore free modulus of elasticity of pore free material. T 0 is a surface energy for pore free material when it is some porosity already existing in the material. So, both this can be written as E 0 into 1 minus p, and this can be multiplied into T 0 into 1 minus p. So, if you take it out, this will be the constant and 1 minus p will come out, and critical stress will be something like this. So, therefore, from this it can be understood that the strength is a function of porosity. Higher this relationship is too simple, but still it is good to understand qualitatively that higher the porosity, strength will be lower, and more the larger the pore sizes, strength will be again lower. So, critical stress, because critical stress is related to this. Now, when does so one can possibly write compressive strength is a function of this critical stress, critical tensile stress as well, because compressive failure is also failure due to tension in transverse direction. So, with all this, one can empirically relate sigma c to 1 minus p divided by under root r m. This is a simple relationship, qualitative, just to understand that compressive strength, cube compressive strength or cylinder compressive strength will be a function of the porosity of the concrete, and also a function of root over mean radius, some sort of mean radius which we are calling as mean distribution radius, and there has been relationship developed along this direction, while putting this as a cement content or various other factors, etc., etc. So, one thing is understood, most important, what I would like to point out here is the strength of concrete increases as porosity increases and pore size decreases. Strength of concrete increases as porosity increases, and pore size, strength of concrete increases as porosity decreases. Strength of concrete increases as porosity and pore size decreases. Yes, I think that is what it is. Strength of concrete increases as porosity and pore size decreases both. So, if porosity decrease, strength will increase, pore size decrease, strength will increase. This is what we must understand. That is the fundamental. That is fundamental. All right. Now, volume of pore and pore radius, one can actually, obtain from what is known as pore size distribution curve. I will not go into the basis of this, but what I would like to tell you that the volume of pores can be related to this mean radius, some dispersion coefficient, and overall porosity. So, volume of porosity corresponding cumulative volume of porosity can be related to mean distribution radius. B can be expressed, B is the cumulative porosity at any point. So, intruded volume from mercury intrusion porosimetry, but let me say this is cumulative porosity. Cumulative porosity can be related, cumulative porosities from small pore size to other pore size. So, porosity can be related to cumulative porosity can be related to pore size and mean in terms of mean distribution radius and overall porosity. Okay. And therefore, I can express this is called mean radius, which was same as r m, this r 0.5, median radius equals to r m, or it is called mean distribution radius, B is the volume fraction of pores at radius r, and this is some dispersion coefficient, this is overall porosity. All I am trying to point out that porosity, this there can be a relationship existing between cumulative porosity and r, and from this what happens? You can actually obtain ln r versus cumulative porosity. This sort of curve one can obtain, but what is its implication in our case? we can actually find out the porosity by assuming simple model. For example, this is the cement, this is the water all outside, and we can R 0.5 and D we can express to mix factors. So, through some models, and then if I know R 0.5 as a function of, let us say, W by C, degree of hydration, etcetera, age, T, etcetera, then I can get the full pore size distribution, and we know that R 0.5 is related to strength, this is related to strength, this is related to strength. So, therefore, I can relate strength to, I can actually relate strength to, strength can be related to, strength can be expressed as a function of W by C, H and T, because strength is a function of F R 0.5, and phi. Now, phi can be estimated from Power's model. R 0.5 if I can relate to water cement ratio, degree of hydration and time, then I can relate strength to all this. So, it is possible to use simple model to arrive at R 0.5 and D as a function of water cement ratio, and this just as a qualitative term. I do not think I will go into the expression of algebra, but what I had mentioned is that R can be related to, this is the degree of hydration alpha, degree of hydration alpha. This can be related to age and water cement ratio, and R capillary, mean capillary porosity can be related to water cement ratio and age, and overall R 0.5 also can be related to overall R 0.5 for the gel pores, it can be related, R 0.5 can be related to water cement ratio, because this is related to water cement ratio and this is also related to water cement ratio and time, age. So, using this kind of a model, one can calculate the segmentation age. If you remember, we talked in terms of curing, and theoretical and estimated segmentation age seems to match somewhat. Anyway, that is not my concern, but I am trying to point out that R 0.5 can be related to water cement ratio. That means, the pore size is related to W by C, porosity is related to W by C, age and T, that is age is T, and degree of hydration, age is T and degree of hydration. Now, degree of hydration itself is a function of W by C and T. So, degree of hydration is a function of, so therefore, porosity and pore size is related to water cement ratio and we have seen that pore sizes, mean pore size and porosity govern strength. Hence, strength is governed by water cement ratio and age. So, just let me put it in words now. Let me put it in words. You see what we have seen, the R 0.5 is a function of R 0.5 gel to some gel porosity, and it is a function of water to cement ratio and age. Similarly, R 0.5 capillary is also a function of water to cement ratio and age, and we know the porosity itself is a function of water cement ratio. So, in other words, what we are trying to say qualitatively, quantitative we can leave out. What we are trying to say is strength of paste depend on, of course, bond and number of strength, but it is mostly dependent on porosity and pore sizes. This will be the main contributive factor in normal strength concrete, and capillary porosity and total porosity is dependent on water cement ratio, that is what we have seen, and pore size is also governed by water cement ratio. That is what just now we have seen. So, pore sizes, both pore sizes. So, porosity increases with W by C, pore size increases with W by C, and if porosity increases, pore size increases, strength decreases. Hence, strength will decrease. Hence, strength will decrease. So, that is what is Abraham's law. Total porosity determined. So, strength is governed by water cement ratio. That is what is given by Abraham's law, and Abraham's law is something like this. Strength is a function of inversely, it is a kind of reduces with water cement ratio. These are two constants. So, why does it reduces water cement ratio? Because higher the water cement ratio, my porosity will increase, and my mean distribution radius will also increase. And we have seen that strength is a function of porosity. Higher the porosity, strength is lower, 1 minus p. Higher the mean distribution radius, strength is lower, because it is related to under root 1 over under root mean distribution radius. So, that is why strength is a function of water cement ratio. That is what was discovered by D. A. Abraham in 1920s and 30s, very early 20s actually. So, gel pores, what are the pores in cement based material? I think I have talked about this earlier. Gel pores is one of them, capillary pores in the cement paste. You can see the orders, and macro pores due to air entrainment and poor compaction. So, all this will affect the strength, right. All this will, this of course affects the strength less, because the size is very small. So, because larger size pores affects the strength, therefore, their effect on strength is less, but they actually has a bigger role in shrinkage and creep. And of course, in concrete you will have ITZ porosity, and this ITZ porosity comes because of wall effect, which we have already talked in relation to when we are talking of aggregate packing, right. So, at the boundary of the aggregate you will not have good packing of the cement particles. Then one sided hydration product will grow from the bulk paste side, not from the aggregate side. And if shrinkage occurs, paste shrinks, aggregate do not. Bleed water has a tendency to come up because its specific gravity is low, and if it gets stepped below an aggregate, there will be bleed water tapping. So, therefore, bleed water trapping and all this makes this zone, as we talked about aggregate mortar interface, this zone vulnerable. Actually, there the porosity is more, there the porosity is more. So, porosity is more here, more porosity, more pore, because of wall effect. Hydration growth will take place for cement particle. If I have a cement particle here, it will go from cement particle here, their packing will not be very good, and hydration will take place more along this direction, very little along this direction. Shrinkage occurs, shrinkage will occur there. So, even before your any load has been applied, even before you have applied any load, you might have some sort of a fissure existing here. You might have some sort of fissure existing here, because you will have materials there. So, therefore, you will have fissures or plate like pores existing there. If the bleed water coming and getting trapped here, bleed water coming and getting trapped here, bleed water coming and getting trapped here, because some water trying to go up, it gets trapped here. Then you will have again some sort of fissure existing there. So, they are the one which starts they are the one which are the actually from where my fracture starts propagating, because they are the largest size pore, and from there fracture starts propagating, join some of the pores in the bulk paste, and when all of them have joined, actually overall fracture will occur. So, let us progress further. We have understood that therefore, ITZ porosity, the strength of the concrete is governed by ITZ, because they will have the largest porosity up to about 70% of ultimate load. Cracking is largely due to ITZ cracks, because ITZ would have larger fissures and from there crack starts propagating. As we said, it extends around 30 micron from the aggregate surface, and bleed water trapping below aggregate mentioned in connection with bleeding. If we have not talked much about bleeding, but I have just explained you right now, because when bleeding occurs, because you see the concrete is made up of materials having different specific gravity. Cement has got a specific gravity of 3.15, aggregates will have something in between if I am not using very heavy aggregate like hematite in heavy concrete. So, in ordinary concrete, aggregates will have around 2.6, 2.7 or at best 3 as a specific gravity, but water is 1. So, it will have a tendency to come up all the time, and if it gets, in case where heavy bleeding is occurring, high water cement ratio system, cement is not able to hold the water, water will have a tendency to come up and it might get trapped below the aggregate. So, if it gets trapped below the aggregate, that will be a fissure. All this we have just mentioned a few minutes before. So, therefore, bulk paste porosity and pore sizes, they are governed by water cement ratio, that is what we have seen. And since water cement ratio governs, ITZ porosity is also more and pore sizes are larger, and this is also governed by water cement ratio. Larger water to cement ratio, bleed water trapping chance could be higher, the shrinkage effects, and even the porosity in the ITZ is always more than the bulk paste porosity. High water cement ratio means bulk paste porosity is more, ITZ porosity will be still more. So, it is that is what governs the strength in the normal concrete. Hence, concrete again, therefore, concrete follows Abraham's law. So, cement paste follows Abraham's law, mortar will follow Abraham's law, and concrete will also follow Abraham's law. And that is because higher the water cement ratio, I will have more pores in the system, because we have seen in the in the earlier modules that capillary porosity is a function of water cement ratio. More the water cement ratio, more will be the capillary pores. When we looked at the hydration process, if you can recollect, we are talking about expanding cluster model, more water cement ratio, more pores, more capillary pores, and size of the pore will also increase with water cement ratio. That is what we have seen today. Therefore, higher the water cement ratio, strength will be lower, both for cement, concrete and mortar as well. And this is what possibly the next diagram will show. This diagram will show paste strength or mortar strength or anything of that kind. Water cement ratio, higher the water cement ratio, compressive strength reduces, higher the water cement ratio. So, therefore, this is the fundamentals. So, water cement ratio is the fundamental one which governs the strength of concrete, and that is what we have understood today, right. And why does it affect? Because higher the water cement ratio, I will have more capillary porosity, my pore sizes will be larger, right, and size of the pore governs the strength. Larger the size, critical stress required to initiate fracture from that pores will be smaller, which means that crack will start generating first and propagate again faster. And also we have seen that compressive strength is actually compressive failure is because of tensile failure again. So, therefore, this is what we have understood. We will see the role of aggregate and other things in the subsequent classes. So, we have essentially seen the role of paste, role of ITZ, mainly role of porosity and water cement ratio. So, I think the first lecture gives us this idea why strength is a function of water cement ratio. It is very important to understand that strength in all this kind of material decreases with increase in water cement ratio. So, therefore, trick in getting high strength concrete is using reduced water cement ratio, reduce it as much as possible, keeping in mind that you have to also take care of the workability. We said earlier that below the consistency, standard consistency, the water may not be sufficient to make the flowable paste flow, not at all, it will remain dry, inconsistent paste. So, these issues are there. but the technique of getting high strength concrete therefore revolves around this issue, this understanding that lower the water cement ratio, lower will be the porosity and pore sizes, and that is the way, from that only we proceed towards high strength concrete. Anyway, high strength concrete is not the issue at all. At the moment we are looking at normal strength concrete. So, today we have understood role of paste essentially, ITZ, and mainly we have looked into this. So, next class we will look into aggregate and other factors. So, with this, thank you very much.